Thank you for joining us today for the RGEM speaker series. I am Lindsay Beecham with the University of Idaho Water Resources Research Institute in Coeur d'Alene. The RGEM Coeur d'Alene Lake Collaborative is a team of professionals working to preserve lake health and protect water quality by promoting community awareness of local water issues through education, outreach, and stewardship. We have representatives from the University of Idaho Water Resources Research Institute, the Coeur d'Alene Tribe, Idaho Department of Environmental Quality, Kootenai County, the Basin Environmental Improvement Project Commission, Kootenai Environmental Alliance, and the Coeur d'Alene Regional Chamber. In addition to these online speaker series, we guest author water-related articles in the Coeur d'Alene Press every other Sunday. You can find the archives of past presentations and articles on our website, uidaho.edu/rgem. Our speaker today is Lauren Zinnser. Lauren is a supervisory hydrologist and water quality specialist at the USGS Idaho Water Science Center in Boise. Her research focuses on field studies of surface water and groundwater resources, including long-term water quality monitoring, trend analysis, groundwater characterization, and the biological uptake of contaminants. You may ask questions in the chat at any time, but we'll save them for the end. Questions will be prioritized by relevance to the topic at hand. And if we run out of time, feel free to email us your questions. I can drop an email address in the chat, and then we will follow up with them as soon as we're able. So with that, Lauren, if you want to turn it over to you.
Sure thing. Well, first of all, thanks for having me, and thanks to all the folks who organized and attended the speaker series. As Lindsay said, I'm Lauren Zinnser, a supervisory hydrologist at the USGS, and I'll be talking today about long-term monitoring work that the USGS does in cooperation with the EPA at the Bunker Hill Superfund site. And then also how we use these data to understand the effects of the cleanup and to guide future cleanup as well. So diving right into it. As many of you know, if you're on this call, the Silver Valley was a huge metal producing area in the Coeur d'Alene Basin for many, many years. And so the Coeur d'Alene Mining District is shown here, roughly outlined in the red dashed lines. Lead and silver ore were first discovered in Canyon Creek in 1984. The Bunker Hill mine was started by Noah Kellogg in the fall of 1885. Over the subsequent 100 years, more than 100 mines produced approximately 130 million metric tons of lead, silver, and zinc ore. While it was in production, it was the largest and richest silver producing region in the world. It was estimated in 1997 that the total value of the metals extracted exceeded $26 billion. The production shifted over time in relation to how technologies were changing and then also world events. And so you see here, there's ore in megatons on the left axis, metals in megatons on the right-hand axis, and time along the bottom. So when production first started in 1885, it ramped up. It ramped up through World War I. It then dropped off through the Great Depression. It increased again through World War II and the post-war boom era before kind of slowly tapering off to modern times. Technologies also changed over that time. So initially, metals were extracted using jigs, which was basically a process to crush the rock into fairly coarse fragments from which the metals were extracted. This left a lot of metals behind in those tailings waste. Over time, the technology changed to flotation, where the ore was crushed into much, much finer sizes, which produced fine tailings, and then they were mixed with chemicals in order to float off the metals and to separate them in that way, and that produced a much finer waste. And then tailings were released directly into the streams all the way up until 1968. The first lawsuit that was brought against the mining companies for the effects of those tailings was in 1903. So obviously a tremendous amount of metals extraction, which brought a lot of value to the community, but also brought with it immense environmental damage. So tailings were intentionally released into the rivers. The river were used as the disposal system, washing them downstream and away from the mining areas. At the same time, timber cutting also boomed along with mining, and this was to produce the houses, to produce the wood to build the houses and everything else in that area. So that meant that also took took away a lot of the forest on the hillsides, which also increased hillside erosion during that time. Smelting produced localized acid rain, which also killed trees and vegetation. And all of those things had a pretty grave impact on the environment over time. These wastes were transported vast distances downstream. So the stream itself carried the tailings downstream, but then when you had flooding events that washed stockpiled materials, it washed those materials even further. And so many of those materials, you can see in here, the flooding pictured in 1993, for example, through the town of Kellogg, those tailings and other wastes were deposited way downstream along the main stem Coeur d'Alene River, where the gradient grows a lot flatter, and you have those complexes of lateral lakes and marshes and wetlands. So the mining happens again in this kind of outlined area, and then the wastes themselves were washed downstream, coming to rest along the main stem Coeur d'Alene River in this complex of wetlands and lateral lakes. The wastes were also washed into Coeur d'Alene Lake and all the way downstream into the Spokane River and further. The metal-laden sediments are harmful to people and animals. As early as 1900, downstream farmers complained about leaded animals. Lead, of course, is a neurotoxin, which affects human mental and physical development, especially for kids and pregnant women. These sediments contained metals, including, accumulation of lead in wildlife can also kill wildlife. For example, by paralyzing the guts of swans. And then zinc and cadmium can also kill aquatic life by interfering with their mineral balance. Essentially, it prevents aquatic life from taking up calcium, which is a major part of keeping their bodies working and balanced over time. So the widespread dispersal of these mine wastes and extraordinarily high blood lead levels in children in the Silver Valley eventually led to the listing of the Bunker Hill Mining and Metallurgical Site on the National Priorities List for cleanup in 1983. The initial listing was for a 21 square mile area around the towns of Kellogg and Smelterville. Cleanup began in 1986 with fast track cleanup of public areas within that box, what is known as the box, that 21 square mile area. The record of decision for the populated areas of the box was first published in 1991. Record of decision is basically a really important document published by the EPA that documents what the contaminants are, what approaches have been evaluated for cleanup, and what approaches are going to be implemented for the cleanup. And so they really guide how remediation and cleanup happens. A record of decision was published for the non-populated areas in the box in 1992. In 1998, with the recognition that mine wastes were spread throughout the basin far beyond that initial 21 square mile box, the EPA initiated the Superfund process for 1,500 square miles outside the box, which is known as operable unit number 3. The interim record of decision for cleanup in that area was published in 2012. So all of this is to say that at this point, the EPA has spent over 40 years studying and advancing cleanup of the site, but there still is a lot of work that remains to be done. So in the meantime, the USGS has been conducting surface water monitoring beginning as far back as the 1970s and increasing in scope in the 1990s as the cleanup began to pick up speed. Finally, our monitoring was consolidated under the Basin Environmental Monitoring Plan in 2004. The Basin Environmental Monitoring Plan, or BEMP, is basically the consortium of folks who are doing environmental monitoring for the EPA to inform cleanup. The goals of our part of the BEMP are to determine concentration and loads in the surface water, to detect trends and constituents in the surface water, to use these data to make inferences about how the cleanup is going and what processes are happening in the river, and then ultimately to evaluate how the cleanup is going or the effectiveness of the cleanup. So there are multiple components to the monitoring that the USGS does, but one really important part of it is our provision of long-term stream data. And so the USGS has many gauging stations throughout the river basin. I'm highlighting only a few here in orange because I think they give a sense of the length of the records available. The oldest gauges are Cataldo, the Coeur d'Alene River at Cataldo, and the North Fork Coeur d'Alene River at Enaville, and gauging there began in 1911. So that's a pretty long time. More gauges came online, especially in the South Fork Coeur d'Alene River in the late 1980s, associated with characterizing streams in the Superfund area. The newest gauges are at the mouth of the Coeur d'Alene River near Harrison, the St. Joe River near Ramsdale, and the outlet of Coeur d'Alene Lake, which is in the Spokane River. This is because all of these sites are periodically affected by backwater conditions from the raising lake levels and are therefore more difficult to monitor flow. All of the data for these, of course, are available on our website, NWIS, which is linked there, or that you could Google that and find that pretty readily if you were so inclined. So a little bit more on discharge data. The USGS gauging stations don't actually directly measure discharge. Instead, they actually measure stage, which is the height of the water, or water velocity. These parameters are then related to discharge by making periodic discharge or stream flow measurements at the site by a technician, which are then used to develop a rating curve that correlates the stage and velocity or velocity to the discharge. Most of the gauges in the basin are stage gauges, but the backwater affected sites are actually index velocity gauges that use acoustic Doppler velocity meters, or ADVMs, which is shown in this lower picture down here. The USGS started using these in the early 2000s, and these gauges were installed in the Coeur d'Alene River near Harrison, St. Joe at Ramsdale, and the Spokane River at the lake outlet. They're a much more useful technology in a place where there's backwater, because backwater, in a place that is backwatered, where the water rises in relationship to the dam, higher water doesn't necessarily mean faster water the way it does at a stage gauge. And so that's why we use this different type of technology at those backwatered sites. So in addition to discharge, we also collect water quality samples. Again, this is not a comprehensive map of all the different sites in the basin at which we have water quality records, but it gives you a sense of some of the water quality records that are available. So we've been collecting water quality starting as far back as 1971 at sites within the basin. As I mentioned earlier, this sampling was consolidated with the EPA's BEMP in 2004, and so there's a little bit more standardization in what we collect and where from that point forward. All of these data are available online, of course. So a little bit more on the sample collection. Our water quality samples are collected using standardized collection methods. The samples are isokinetic, which basically means that the velocity of the water entering a sample nozzle, so this is a picture of a sample or a diagram of a sample nozzle here, the velocity of the water entering the sampling nozzle enters at the same speed as water that is flowing on either side of the nozzle. And that's important because that means that we are sampling the same concentration of constituents in the water as are in the water flowing around. If the water flowing into the sampling nozzle is a little bit faster or a little bit slower than the surrounding water, you can bias your sample, which is to say that you can get a concentration entering your sampling device that's different than the concentration in the water around it. So all of that is to say we take a lot of care in the way that we collect samples to make sure we're getting a representative sample at a site. The other way in which our samples are collected is with in-depth integration. So basically this means that we take a sample at multiple locations across a stream cross-section. The amount of water collected at each location is proportional to the amount of flow in the stream in that place. And so basically if there's more water flowing through the stream in this interval, then more water is collected. All of that water gets collected in one big churn splitter, so one big other container, and mixed together and then subsampled, which I'll go through in the next page a little bit. But again, all of this is to say that we put a lot of work into making sure that the samples that we collect from a stream are fully representative of the constituents that are flowing through that stream, even if the constituents are not evenly distributed across the stream channel. For the BENT program, we collect samples 2 to 12 times per year in a variety of hydrologic conditions, with emphasis on events where there is high stream flow, because a lot of stuff tends to be moving at those times. We've measured a lot of analytes over time, including total infiltrated metals, total infiltrated nutrients, cations, and suspended sediments. Here you see a picture of the bridge crane instrument, and then the sampler on the front. This is the piece of equipment we use to lower that sampler up and down through the water column and across the full length of the bridge. Samples are composited in the churn, which is actually sitting in this bucket back here, and then they're brought into our mobile lab, where we then split off samples to be sent to the lab for analysis. Samples are often processed under a chamber, which is to avoid contamination with any constituents that may also be in the air around us. So over many, many years of sampling, what have we learned? We've learned a lot. So one of the big things is that sediment-laden floodwaters can transport vast amounts of particulate metals, especially lead. Dissolved metals, on the other hand, in the groundwater impact surface water quality all year round, and metals are transported into Coeur d'Alene Lake and downstream into the Spokane River. So a little bit more on some of the general things that are happening. Here there's a few graphs. Concentration is on the vertical axis. Stream flow is on the bottom axis. This is for the South Fork Coeur d'Alene near Pinehurst, which is the station that's basically very close to the mouth of the South Fork Coeur d'Alene River. There's pictures of it at a couple of different flow conditions over here on the right. Both of those are actually relatively high flows. And you can see that in this far left picture, total lead increases with more discharge. So basically, the more stream flow is running, the more lead is being transported. Phosphorus is similar to an extent. We see higher concentrations of phosphorus at higher flows, but we can also see higher concentrations of phosphorus at low flows too. And then dissolved zinc, on the other hand, is pretty much the opposite. We see the highest concentrations of dissolved zinc at low flows, and concentrations of dissolved zinc actually decrease with higher flows. In contrast, at the Coeur d'Alene River near Harrison, which is the mouth of the Coeur d'Alene River right before it flows into Lake Coeur d'Alene, we again have the same graphs, and we have some of the same relationships. We see that lead concentrations go up with higher discharge, and some of the really big floods, like the one of 1996, for example, produced the highest lead concentrations we've measured in the river. The same is true for phosphorus down here. We don't really see that low flow signal for phosphorus in the Coeur d'Alene. We see higher flows, we get higher phosphorus. And zinc, the highest concentrations of zinc are at the lowest flows, which again points to the importance of groundwater inputs for dissolved metals. So now hold on a minute, right? Like, what's phosphorus got to do with it? So far I've talked about metals, but phosphorus is also a constituent that folks are interested in this system. So phosphorus comes from both point and non-point sources. Point sources are things like the wastewater treatment plants, also the former fertilizer plant waste. And so that's actually a mining-related waste stream. There used to be a fertilizer plant in the Smelterville area, and the wastes from that production plant are part of the waste package in the central impoundment area, and they are releasing phosphorus into groundwater, and they are impacting phosphorus. So there are mining-related point sources and also non-mining related sources like the wastewater treatment plants throughout the basin. There are also non-point sources, and so that would be phosphorus that doesn't come from the end of a pipe necessarily, but just comes from everywhere. And so that would be soil, include things like soil erosion from forests, also stormwater runoff. And why do we care about phosphorus? phosphorus is a concern for water quality in Lake Coeur d'Alene. So many of you probably know if you get too much phosphorus in a lake, you can get too much growth of plants and algae, which when they die, decay and take up oxygen, which can leave too little oxygen in the water to sustain fish and other life. So this is bad for fish. It's also bad for humans who like to recreate in these waters and don't want to recreate in these really scummy waters that are overgrown. But it's also especially concerning for Coeur d'Alene Lake because of all of the metals in the sediments at the bottom of the lake, which could potentially be released into the overlying waters if the dissolved oxygen or the pH in the lake changed significantly, which is a concern with increased phosphorus. So phosphorus is also something that we are paying attention to. So over the last 40 years, the EPA has used the data that we've generated to do a lot of cleanup work, also data generated by other folks too. This work started in the box around the area of Kellogg and Smelterville, where the Bunker Hill smelter used to be. This included things like taking down the smelter, capping the central impoundment area, which you see over here, diverting streams, removing wastes, and hardening stream banks to prevent erosion. Cleanup has also continued outside of the box, including on tributaries like 9 Mile and Canyon Creek, where again, tailings and wastes have been removed from the stream channel and placed in repositories. They've regraded hillsides to reduce erosion and regraded streams to be more functional. A lot of this similar work has been done in the vicinity of Osborne Flats as well. You can see a pretty dramatic series of photos down there. And then work has also recently been completed in the central impoundment area, where they installed a groundwater collection system to intercept groundwater that was carrying dissolved metals to the stream, treat them at their upgraded wastewater treatment plant, and then release cleaner water into the South Fork Coeur d'Alene River. So, oops. Oh, but limited remediation has happened so far in the main stem of the Coeur d'Alene River for a variety of reasons that we'll talk a little bit more about later. So we've learned a lot from monitoring, but given all the remedial work that has happened, we still have a lot of questions about the area. This includes pretty basic questions like, have concentrations and loads of the constituents of concern gone down? Are concentrations and loads still going down? Have the major load sources changed? And are concentrations still harmful to people and critters? So to address these questions, I used basically what I could summarize as fancy statistics, but more specifically, I used weighted regressions on time, discharge, and season. WRTDS is a highly flexible regression approach that uses the relationships between concentration, time, discharge, and season to estimate concentrations during each day of the period of study. These estimates can then be used to estimate flow normalized annual mean concentrations and annual total loads. So all things equal, loads tend to scale with flows. And so in a low flow year, you have a lower load, and in a high flow year, you have a higher load. So what flow normalization does, in effect, is estimate what concentrations and loads would have been for a given year if the hydrologic conditions have been average. So this approach is really helpful for trend detection because it smooths out some of the year-to-year variability that's associated with high and low water years. I also use WRTDS with Kalman filtering to estimate annual mean concentrations and annual total loads. This approach provides the best estimate of actual annual conditions because this model is forced to respect actual sampled concentrations. And then finally, I also used a bootstrapped approach to model concentrations over time, many times over and over again, which is used to construct confidence intervals around the trends. These data are then used to describe the statistical likelihood of change over time. So moving on, to construct these models, these fancy statistical models, I used USGS water quality monitoring and discharge data from 3 sites that I'm going to talk about today. I actually did this for a whole bunch more sites than this, but just today I'm talking about 3. 3 I'm talking about today: South Fork Coeur d'Alene River near Pinehurst, which again is at the mouth of the South Fork Coeur d'Alene River, the Coeur d'Alene River near Harrison, which is at the mouth of the Coeur d'Alene River, and then the Spokane River below the lake outlet. including data for water years of 1990 through 2018, although the actual period of record varies a little bit at these different sites. And this presentation is drawing on a much bigger body of work that modeled many more sites and constituents, but I'm just focusing on a few sites and a few constituents today. So before I go any further, I also just want to pause and take a minute to acknowledge how much data this actually reflects and how many people were involved in collecting this data and funding this data over time. So, for example, the samples I use in this analysis were collected back before I personally could read or write. It was collected at a time when USGS reports looked as though they were typed on typewriters. I'm not sure if they were or not. And our figures looked more like hand-drawn line drawings. And when the sampling equipment was actually the same, but what we wore was maybe quite a bit different. And so I just, again, want to take a moment to acknowledge all of the USGS staff who have collected the data, rain or shine, over the last 30 years, and in fact are out on the landscape today up there, where I think it's still raining and snowing, collecting data. And also for anyone who's in the audience who has advocated for this monitoring or even funded this monitoring. None of this analysis and none of what I'm presenting can be done without all the people that have contributed to it. So big thanks to all of them. So over the last 30 years, the sampling equipment may have remained the same, but have the concentrations and loads gone down? So I'll walk you through the graph and you'll see more of these. Dissolved zinc concentrations is on the left, in micrograms per liter, is on the left-hand axis. The flow normalized concentrations are shown in the line. On the right-hand side, we have dissolved zinc load in metric tons per year. Again, the flow normalized concentration is shown in the line, whereas the best estimates of the actual annual concentrations are shown in the black dots. So at the South Fork Coeur d'Alene River near Pinehurst, the answer is a pretty dramatic yes. Concentrations and loads have both gone down dramatically over time. Moving further downstream to the Coeur d'Alene River near Harrison, again, we see very dramatic declines in loads and concentrations over time. We also see similar declines between below in the Spokane River below the lake outlet. So overall, dissolved zinc concentrations and loads decreased 35 to 65% over the period of record. For lead, total lead, have concentrations and loads gone down? The answer is in some places yes, and others no. So in the South Fork Coeur d'Alene River near Pinehurst, concentrations and loads have gone down. They've also gone down in the Spokane River below the lake outlet, although a little bit more modestly. But the story is a little bit different at the Coeur d'Alene River near Harrison, where concentrations have kind of gone up and down and loads have actually gone up slightly at the Coeur d'Alene River near Harrison. But you also might have noticed that in both of these graphs, the decrease kind of flattens off a little bit at the end, which will lead us into our next question in a minute. So before I get there though, for phosphorus, have concentrations and loads gone down? Answer is, it really depends. Concentrations actually and loads increased sharply at the South Fork Coeur d'Alene River near Pinehurst, and then sort of tapered off in the last decade at both Pinehurst and near Harrison. They have mostly gone down at the Spokane River near the lake outlet. But you might notice too, there's also a really big difference in record length here. The reliable phosphorus data goes all the way back to 1990 for Pinehurst, but only to 1999 for Harrison and 2003 for the Spokane River. So this leads us to our next question. Are concentrations and loads still going down? So to get at this, I looked more closely at the rate of change in load per year in two discrete periods. I'm only looking at two sites here, the South Fork Coeur d'Alene near Pinehurst and the Coeur d'Alene River near Harrison. So the vertical axis shows the slope of the change in load expressed as a percent per year. The data were broken into two periods for comparability. 1999 through 2009 are shown in red, and 2009 through 2018 are shown in orange. The dot represents the median slope, and the bars represent the 90% confidence intervals. For dissolved zinc, which is shown on the left graph here, the change in load is really strongly negative at both periods of time, although it is somewhat less negative in the second period of time. And so what that means is that the load is still decreasing, is decreased faster from 1999 to 2009, but is still strongly declining in 2009 through 2018. This is also true for total lead at Pinehurst, which is shown over here. It decreased during both of those periods, although it decreased faster earlier. But it is not true for the total lead load, which actually increased at Harrison during that first period of 1999 through 2009, and then was basically around zero, or had no change, no statistically significant change during the second period of time here. So I believe I just talked myself through that. So for phosphorus, our concentrations and loads still going down. Again, using the standardized time intervals, you can see that the South Fork Coeur d'Alene near Pinehurst, which is right here, that phosphorus went up a little bit in the first period of time and then went down in the second period of time. This is also true, although somewhat more dramatic, a stronger positive increase in the North Fork Coeur d'Alene at Ainaville during the first period, and a stronger yet increase in phosphorus at the Coeur d'Alene River near Harrison during that first time period. In the second time period, we see decreases in those trends. And so again, we sort of have a shift. First, we had increasing phosphorus at these sites, and then we had decreasing phosphorus at these sites. So moving on to the next big question, or I guess this is big question number 1 and number 2 continued. How statistically confident are we in these trends? Because of course, it's one thing to see a downward line on a graph and say it's decreasing, and it's another thing to show it statistically. So in order to get at statistical confidence, I used a bootstrap technique to construct the WRTDS models many times for every site and constituents. And then I came up with a graph that looks a little bit like this. So if, for example, the trend was down in 85 or more of the models, assuming that I ran 100 models, then the trend is considered likely down and is shown with a solid blue arrow. If, on the other hand, in 85 of those 100 models, the trend was up, then it would be designated with a red upward arrow, meaning it was a likely up. If the trend was down in 70 of those models or more, then it would be somewhat likely down. The size of the arrow is indicating the magnitude of the change. So the biggest arrow size means a change of 51 to 80%. So here again, you're seeing the statistical confidence. And so for dissolved zinc, which is shown here, over the dissolved zinc concentration over the period of record, and dissolved zinc load over the period of record, and the lower graphs are 2009 through 2018, 2009 through 2018, with load on the right and concentration on the left. Through all those periods of time, we see that the dissolved zinc concentration and load decreases are statistically likely at all 3 of those sites over both the period of record and through the 2009 through 2018. So again, basically, yes, we are very statistically confident that we have downward trends at all of these sites over both of these periods of time. So now moving on to lead, same graphs, but we see that the symbols are a little bit different. We see that the total lead decreases are statistically likely over the period of record, which are these 2 graphs. Again, the concentration and load over the period of record. And over the most recent decade, they are down at all of the sites except for the Coeur d'Alene River near Harrison, where there's actually slight increases in the total lead load over the period of record. So this sort of begs the difference. Why are there strong differences in the trends between the lead and the dissolved zinc? But we'll get there in a minute. So one more thing to look at before we get there is phosphorus. So how statistically confident are we in the phosphorus trends? The answer is we are statistically confident, but there's a lot of variability in the trends over the entirety of the site. And so at some locations, we have increases. For example, the South Fork Coeur d'Alene at Pinehurst over the period of record, we are statistically confident that there are strong increases in the concentration over the period of record. We are similarly confident, but lower concentration increases at Harrison over the period of record. But over the last decade, we actually have downward trends at Pinehurst, but not necessarily at Harrison. So there's a lot of variability in what's happening with phosphorus concentration and loads. throughout the basin over this period of time. So the next question is, have the major load sources changed? And this has a lot to do with the sources of all the different things. So previous research, which I talked us through a little bit at the beginning of the presentation, has shown that most of the dissolved zinc in the system comes from the South Fork Coeur d'Alene River, with major sources including the Bunker Hill Box in the vicinity of the Central Impoundment area, and tributaries like 9 Mile and Canyon Creeks, where a lot of work has also been done. In contrast, most of the total lead came from the main stem Coeur d'Alene River, where again, that low gradient meandering river floodplain and the lateral lakes have trapped a tremendous amount of particulate lead that was previously transported down from the mining district in big floods and other flooding events. In contrast, phosphorus kind of comes from all over the place. It comes from the forests, it also comes from the CIA, it also comes from wastewater treatment plants. And so knowing all these things about where these different constituents are coming from, and knowing that some of these things have been cleaned up and targeted over time, how have the sources of these constituents changed over time? So starting with zinc, on the vertical axis here, we have the annual total load of dissolved zinc in metric tons. We have water year along the bottom. The total load from the South Fork Coeur d'Alene River in Pinehurst is shown in purple. The total load from the stretch of the river between Pinehurst and Harrison, which is the main stem Coeur d'Alene, is in green. And then yellow shows the amount exported from Coeur d'Alene Lake. So basically, a couple of the things we see, the vast majority of the load is coming from the South Fork of the Coeur d'Alene River. About the same amount of load that is going, or most of the load that goes into Coeur d'Alene Lake, shown in green, actually exit Coeur d'Alene Lake from the Spokane River. But we also see that those loads are decreasing during time, but the South Fork Coeur d'Alene does still remain the main source of dissolved zinc over time. And for lead, so here the graph shows the total annual lead load. In this case, it is clear that the vast majority of the total lead load is still deriving from the Coeur d'Alene River, the main stem Coeur d'Alene River. And that the vast majority of this lead actually stays in Coeur d'Alene Lake, because you can see that there's really only a teeny tiny amount that is exiting the lake via Spokane River. So this is illustrated pretty clearly in pictures of the lake inlet coming in, or high flows into the Coeur d'Alene, from the Coeur d'Alene River into the lake are shown here. And then the outlet, much less sediment is transiting out. And so this is pictures taken during a high flow event in March 2008, where you can very clearly see this plume of sediment, which contains high concentrations of particulate lead, entering the lake, and then way less sediment leaving the lake on the other end. So most of the lead gets trapped in Coeur d'Alene Lake. And finally, taking a look at the similar graphs for total phosphorus loads. So unlike the metals, the North Fork Coeur d'Alene and the St. Joe River are significant contributors of total phosphorus. So these graphs are a little bit different, showing the phosphorus in the Coeur d'Alene system and the lake separately. The upper graph here breaks down total phosphorus load from the North Fork Coeur d'Alene in blue, the South Fork Coeur d'Alene in purple, and the total load in the Coeur d'Alene near Harrison in green. So what you see is that generally higher loads come from the North Fork Coeur d'Alene than from the South Fork Coeur d'Alene. But remember, or perhaps I'm telling you for the first time, that the North Fork contributes about 70% of the flow versus 30% coming from the South Fork Coeur d'Alene. So the loads of phosphorus coming from the South Fork Coeur d'Alene are disproportionate to the flow. In high flow years, for example, 2011 here, much more phosphorus comes from the main stem Coeur d'Alene than in a low flow year. So now looking at the loads into and out of Coeur d'Alene Lake. So the Coeur d'Alene River is contributing kind of this teal color, the St. Joe River is contributing the green color, and the Spokane River is exporting the yellow here. And so on average, the Coeur d'Alene River and the St. Joe River contribute about the same amount of phosphorus. During high flow years, the Coeur d'Alene tends to contribute more than the St. Joe. They also contribute about roughly equal amount of water to the Coeur d'Alene Lake. And then the Spokane River exports total phosphorus that's equal to about a quarter of the entering total phosphorus load each year. So in the case of the metals, we understand what's driving those trends, right? We understand that for dissolved zinc, there's been a lot of cleanup in the upper basin, including cleanup of groundwater that's entering the South Fork Coeur d'Alene. So it makes sense that the dissolved zinc is going down, even though the South Fork is a big source of it still. In the case of the main stem Coeur d'Alene River, it makes sense that there's loads are still going up a little bit for lead because of so much of the lead is stored in that lateral lakes area, which hasn't been cleaned up yet. But for phosphorus, the questions about the sources are a little bit less clear. But nonetheless, we have a few ideas about what's going on with the phosphorus and what's driving those trends. So essentially in the South Fork Coeur d'Alene River near Pinehurst, where you may recall, the phosphorus is going up for the first 15 years or so, and then it's kind of leveling off. What do we think is happening there? So basically, this watershed is steep, it's forested. The area around the South Fork Coeur d'Alene River itself is relatively developed with the highway, several towns, and mining impacted areas, all concentrated in this one narrow little valley. So remediation activities, including really significant earth moving, contouring, and revegetation occurred throughout the 1990s and into the early 2000s, as did other redevelopment of land in the valley, including building and road resurfacing. So in aggregate, one idea that we have is that these activities may have increased stormwater and other surface runoffs during the most intensive period of development and redevelopment, with runoff kind of leveling off, runoff and therefore phosphorus inputs kind of leveling off as the vegetation became more established and the surface disturbances decreased. So that's kind of one running idea we have about what could be driving phosphorus trends. In the Coeur d'Alene River, the trend is a little bit different, but of course the Coeur d'Alene River is also a really different system with deeper, slower meandering river and a series of connected lateral lakes and wetlands. So portions of the valley bottom flood during high flow events, like the one pictured here in 2017. So again, I think that the trends in phosphorus here may be related to disturbance, but different than the disturbance in the South Fork Coeur d'Alene. So as I mentioned earlier, there were record floods in 1996 that transported an immense amount of metals in the basin, and the floodwaters inundated much of the valley bottoms and eroded stream banks, deposits, and floodplain soils. So there was no systematic study of the change in the floodplain associated with this event, but it seems plausible that such a significant flooding event could have really impacted the system either by depositing a lot more phosphorus and sediment in the main channel for later transport, or creating better access to the lateral lakes and marshes by scouring connective channels between them and allowing more of that material to be transported later. So in short, we think that these trends might have to do with the big flood in 1996 and sort of the land kind of returning to an equilibrium over time. And that's why the phosphorus is decreasing now. But it's obviously a really complicated system and we're not entirely sure what's driving those trends. So on to the last question, are the concentrations still harmful? So it's great that metals concentrations have decreased a lot and phosphorus is also decreasing, but there's still a lot of metal and phosphorus in the system. So is it occurring at levels that are harmful to aquatic life? So one way to say whether concentrations are harmful is to compare them to the chronic water quality criteria. So the chronic water quality criteria for zinc and lead are site specific based on the hardness of the water and vary by site and sampling event, and so cannot be represented by one number for all sites at all times. Because of that, the criteria are represented here as a ratio, which is to say the water concentration at a site during an event is divided by that site-specific criteria. Numbers greater than 1 indicate that the criteria was exceeded, and 1 is indicated by this the red dashed line on these. And so the water quality criteria ratio for dissolved zinc is shown on the side here. The data for each site is aggregated by 5-year periods and shown by the box plots. But the long and the short of this is to say that yes, the dissolved zinc concentrations in the South Fork Coeur d'Alene near Pinehurst, and the Coeur d'Alene River near Harrison, and the Spokane River below the lake outlet are all still well above the aquatic criteria for dissolved zinc. That doesn't mean that the ecosystems aren't still improving. They are. The criteria aren't like an on and off switch where all is bad when you're above them and all is good when you're below them, but the concentrations of zinc are still potentially harmful to critters at these sites, despite the improvements over time. Similarly, for dissolved lead, previously I talked a lot about total lead. For this criteria, it depends on dissolved lead. So here we're talking about dissolved leads. The water concentrations are still harmful. So dissolved lead concentrations are occasionally above the criteria at the South Fork Coeur d'Alene River near Pinehurst and in the Spokane River, but they are pretty much always above the criteria by a factor of almost 10 in the Coeur d'Alene River near Harrison. And then finally, phosphorus. Are concentrations harmful? Well, that is like a really complicated question. So there are no numeric criteria for phosphorus concentrations, either federally or in the state of Idaho, the way that there are for metals. But what we do know is the lake management plan identified a trigger value of 8 micrograms per liter as an annual geometric mean. An analysis of 2015 to 2018 concentrations done by the Department of Environmental Quality in the lake showed that the concentrations of phosphorus are increasing to concentrations above this trigger value at a couple of different locations in the lake. And so that is, of course, concerning. The National Academies of Science report that was published in 2022 analyzed data through 2020 and identified decreasing phosphorus concentrations in the lake at a few different points during this period of time. So it's a little bit hard to say if it's not a straightforward answer, I guess, is what I would say about the concentration of phosphorus. We don't totally know what's driving phosphorus trends in the basin, so it's possible values could go up again. Although there are also major investments by the state of Idaho that have been made for upgrading wastewater treatment plants in communities that discharge to rivers that feed to Coeur d'Alene Lake. So that is helpful in bringing concentrations down. But there are also in-lake processes that use and release phosphorus that can be independent of the inputs. So long story short, phosphorus continues to be a concern for Coeur d'Alene Lake. So in summary, have concentrations and loads of key constituents gone down? Yes, for dissolved zinc and total lead, which decreased by big percents, 25 to 75% over the period of record. It depends for phosphorus. Phosphorus concentrations and loads have increased and then decreased. Are concentrations and loads still going down? Yes, the decreases are smaller, but still statistically likely over 2009 through 2018 for dissolved zinc and total lead. Phosphorus trends are also mostly decreasing from 2009 through 2018. Have the major load sources changed? No, the South Fork Coeur d'Alene River remains the primary source of dissolved zinc, although it is improving. And the main stem, Coeur d'Alene, remains the primary source of total lead, where more remediation is planned in the future, but hasn't taken place so far. And then finally, are concentrations still harmful? It depends, but generally, we are still concerned about the levels of zinc, lead, and phosphorus in the system. There's tons more information about tons more sites in a report that was published at this point a number of years ago. And then with that, I am happy to take any questions that you might have.
Thank you, Lauren. We have a couple of questions in the chat. So the first one is from Bonnie Douglas. She asked, has there been any flood control added over the years to protect populated areas during high water years?
Ooh, that is a good question. And I don't actually know offhand about what has been done to protect properties from flood control. So I'm sorry, I don't know the answer to that question.
Bonnie, we might be able to follow up with some people and get back to you on that one.
Yep. There are certainly people who know better than I do on that one.
And then Craig Cooper has a comment. He says, hey, Lauren, if anyone asks, we've recently updated the report card with recent data through 2024. Phosphorus now has no trend from 91 through 2004. And that's Craig Cooper with DEQ.
Awesome. Thank you for adding that information, Craig. I love getting updated data.
Felicia Cassidy wants to know if remedy protection programs throughout the valley for flood protection. She can provide more information on that. And there's more to do, she said. So Bonnie, maybe we can get you in touch with Felicia. We have an anonymous person wanting to know if Superfund remediation efforts and USGS monitoring are at risk of being defunded through Dodge.
I don't know. Yeah, particularly I do not know for EPA. I do know that we at the USGS have been affected by various executive orders, but at present, there are not impacts to the BEMP monitoring that is being done, and we hope that that remains true as it's really, really important monitoring.
Are there any more questions? You can also raise your hand. I think that. Oh, one more. Tyler Huber would like to know, how can the city of Harrison help with present and future cleanup near the Harrison Slough? What resources should citizens be provided with to be better informed?
Oh man, that's an awesome question. And I feel as though I'm not the right person to answer that question. I suspect that getting involved with the BEIPC, the Basin Environmental Improvement Commission, would be a great resource to connect to and a great organization to get in touch with. They are sort of the resource that connects citizens to the environmental cleanup activities that are happening. And Sharon Bosley is the lead of that. And so I would point you in that direction.
Yeah, that is. I'm trying to pull up the link to their website.
There was also a comment from Felicia that said they can also call the citizens in Harrison could also call the Panhandle Health District for more
That was going to
information.
be one of my suggestions too.
So thank you,
Yeah.
Felicia.
Okay, let me double check that that is all of them. All right. I think that includes all of our questions, and thank you so much, Lauren, for presenting. This was really informative. And thank you everyone for attending. Next month, we will have Doug Evans, and he will present on Coeur Bay wetland restoration. I'll send a follow-up email with a recording of this so you can share it for those who aren't able to attend. So thank you, everyone.
Thank you.